My name is Mark Shaw, I'm Technical Manager for Sika, and I'm presenting today on corrosion, solutions for corrosion management, the history of structural strengthening and solutions using FRP composites. Okay, we're now going to insight in why concrete deteriorates, why reinforcement corrodes, and I'm going to sort of give you an insight now into how we can try and avoid it in the first place, but if we have got the problem, how we can at least control it, and that may happen by stopping it. Quite difficult to do, but there are ways of controlling it where you can actually extend the life of a structure once it's started to deteriorate. So I'm going to look at concrete repair and the remediation methods that are actually available at the moment, predominantly looking at 1504 Part 9. What we look at from the point of view of total corrosion management and how we can relate that to 1504 Part 9. Our corrosion management portfolio, and then start to look at giving insight into the CE marking or the testing we have to do, what you can look at on the packaging to ensure that it does comply with 1504, and then just sort of tidy that up with a few sort of case studies of how we've resolved a few of the problems in the past. Okay, defects in reinforced concrete. Things you may sort of come across, quite obvious really. You've got reinforcement corrosion, laminates, corrosion takes place, it expands, and it just blows the surface of the concrete off. So it's what we call spawning. This is a structure here, which you can see most of the cover's been blown off. It's in a marine environment. Odds are that's caused by chlorides, that type of corrosion, where this, because it's more generalised corrosion, is generally caused by carbonation. This is something I'll cover in a little bit more detail in a moment, but Chris was talking about repairs, how they were carried out many years ago, where you just cut out the defective concrete, do something to the steel, put repair material in, leave it, and walk away, and hopefully everything works well. Well, this proves it really doesn't. From the point of view, you can see a repair there, and everything around it has started to corrode. So that, which was originally anodic, corroding away quite nicely, and the big cathode, which was the rest of the reinforcement in there, was driving that process. Then what's happened now is that this has become the cathode, and that's driving the corrosion now, which is occurring and bubbling under the concrete cover. Again, here you can see that some situations can be quite drastic, especially in circular columns. It can blow the outside off as well, especially if the links start to come apart. And this is a bridge abutment. Mainly carbonation here, generalised corrosion, and just the cover coming off. So it's really, what do we do when you've got a situation where you've got quite a lot of chlorides causing the corrosion process? Well, what do you do if it's carbonation? And you do treat them slightly differently, because chlorides, as Chris has shown, can be very aggressive, but you can start to do things to reduce the effect of corrosion through chlorides. So if we just take a sort of typical structural element which is started to corrode, could be part of a building. Say in the past, you would break out the concrete there. You would then do some treatment to the steel, be grit blast, put a build protection on there, put the repair back. So what was an anode, which was rusting away, you've now turned that into a cathode. So now what's happened here is this, which was originally a cathode, is now potentially an anode. So if you don't do anything about it, it's going to start causing you problems in a few years' time. And what we tend to find with a lot of structures is that it's normally only about 10-20% that actually deteriorates on the sort of surface area of a structure. And this is what we call the part of the structure which is now deteriorating. It's gone through initiation, it's actually deteriorating. So we've got 90 to 80% which is unaffected, but you're not quite sure, unless you do lots of testing or electrochemical monitoring, what's happening to this. Odds are some of it will be at a certain point in its corrosion process quite well advanced, others maybe just starting, but you don't actually know. So it's very difficult to say, unless you do a lot of testing, like half cells for chlorides doesn't really work for carbonated concrete, but you really want to understand what's happening here, otherwise you'll get all sorts of problems. I'm going to introduce something to you that you may or may not have come across before. It's called the incipient anode effect. And it really is going back to that photo I showed you earlier on, where in the old days you used to sort of do repair and then just walk away and do nothing about it. Well, what happens is you've got all these other things happening. You've changed the electrochemical process here. And so what happens is you've got these anodes which are now incipient, that's going to cause a few issues for you. Now, can be called the ring anode effect or the halo effect, mainly from in the States, but it happens, and it happens in every country. Mainly happens on chloride contaminated concrete as opposed to carbonated concrete. So you can see here that once you do the repair area, you've now changed this into a cathode, and if you don't take everything back to a good steel, you're going to end up with this incipient anode effect. So there are ways of controlling that, and I'll talk about that as part of the sort of total corrosion management approach. So if we look at a sort of typical anatomy of concrete repairs with this schematic, what we have is a problem which may be reinforcement, where it's cracked and caused, sort of corroded and caused a few cracking. It could have already been spalled condition as well. What we want to do is to take it back to a stage where it was as good as when it was first constructed. So we need to sort of do something with the reinforcement and get a good finish on it to sort of match the surrounding concrete. So there's a lot of sort of work we have to do in between times. We have to sort of break back the concrete to get behind the bars to clean the bars of all the corrosion products. And then we need to sort of prepare the sides of the repairs as well, so that when you put the repair material in, you've got a good bond line and you could get good adhesion. And when you've done all that, you can then apply your repair system as well then to give you your sort of final finish. Substrate and surface cleaning normally is, you know, even if it's got coatings or it's not got coatings on, you generally grit blast, or you can use other techniques, hydro demolition techniques. And what we're trying to do is get this, a texture on the surface that will accept, if you are going to have coatings, that it's suitable. Because in 1504 part 2, for instance, it gives you adhesion guidance on what you should be trying to achieve, whether it's a rigid coating or an elastomeric coating. So if you want to put an elastomeric coating on, which basically is a coating that bridges the gaps as they open and close, you need a slightly stronger bond strength than you do for a rigid coating that just sits on top of the surface. So if you're specifying a project, it's important to specify the surface finish you want so you can apply the coating over the top, which may also need a levelling mortar, which is part of the coating system as opposed to the repair system. And the contractor will then start to choose different types of grit sizes to get that surface texture onto the concrete. Or we could use water jetting or hydro demolition with a little bit higher pressure. So the key stages of a concrete repair are, first of all, is to identify the areas which need repairing, and then to basically break out the concrete. That could be with small jackhammers, CP9s as contractors use, or we can actually use hydro demolition again as well. Now, to prepare the area for accepting the repair material itself, 1504 is quite clear in part 10 that you have to angle the repair area. So rather than do a 90-degree cut or preparation, this is at 135 degrees. So you get a slightly longer bond line in there, but also you tend to get a dovetailing effect as well, which tends to hold the repair in there a a little bit better than if it was just at 90 degrees, and it helps a little bit on the cracking side of things as well. If we then start to look at the substrate and steel preparation, water jetting can be used, very useful in chlorides, because not only does it take the corrosive products off the steel, but it also washes the chlorides off the steel as well. Or you can use a pot blaster, which again is using a very fine grit to actually prepare the steel to an SA2, SA2.5. And then it's then a case of applying the repair mortar. First thing we do is put a protective coating on the reinforcement. Could be a barrier coating, particularly if it's chlorides, or it could be an active coating, which is generally cementitious on the reinforcement. And then we just apply the repair material into that void. Now, repair mortars come in sort of 4 classes in accordance with 1504. Part 3, there's R1, which is sort of low strength concrete, up to about 10 to 15 newtons per metre squared. There's an R2, which takes you up to about 20, and then you have an R3, which is up to, I think, about 30 newtons per metre squared. They're classed as non-structural repair mortars. And then you've got R4, which is the structural repair mortar. From our point of view at Sika, we only supply R3s and R4s. We don't really think you'd need 3 types of non-structural repairs, repair mortars on there. And R4, you've got no choice with one particular product, which is, say, a structural repair mortar. And you can either apply them, different techniques, hand-placed applied, or you can use machine applied, and I'll come into the sort of application processes in a few minutes. And then once you've applied the repair, it's a case of finishing that repair off. And depending on whether it's going to be coated, whether it's going to be left in its sort of normal state and then covered with maybe a clear coating, because it may be perhaps a historic building, or it may have a hydrophobic impregnation, then you can tend to sort of work the surface to what you want really, and that will be determined by the contractor, whether he uses a steel float, wooden float, or a plastic float. A lot of the time, to be fair now, to aesthetically upgrade structures, they tend to be coated, and to get a good coating finish on there, normally apply a sort of what we call a sealer coat of cementitious products, which just fills the holidays in the concrete or the pores, or you put a thickness of about 1 or 2 millimeters, which gives you a really nice finish to apply the coating. And then it's just a case of applying the coating for the job. And as Chris sort of suggested in his last part of his presentation, choice of the coating is quite important to sort of decide how long you want protection for, because if you're in a marine environment, then you need a particularly different kind of coating than if you were in a city and you were trying to protect there as well. Also, if you're on a car park, for instance, you want a coating that will be resistant to traffic and also to people movement as well. So protective coating choice is quite important. Okay, application techniques. We have hand placed, we have spray techniques, and we have flowable or cast in place. They're the sort of terms that are used in 1504. Hand applied, there is a particular technique. We train a lot of the contractors that use our materials at our head office in Welwyn Garden City. And so we sort of show them the techniques and also how to use the materials. And a very quick technique is just to use a trowel and apply the material into the void. That's all very well if you've just taken the top surface of the concrete off, but when you've got reinforcement exposed, it's a little bit more difficult. So what you have to do sounds pretty basic, but you literally have to use your hands and force the material behind the reinforcement. But of course, trying to avoid sort of voidage behind there as well, because you really want that reinforcement to be fully encapsulated in the repair mortar, because then that sort of repassivates also the reinforcement bars. Machine applied, 2 methods. There's one method, is a dry spray, And basically it's for high volume repairs, specifically structural as well. So you end up with a machine here which you apply a sort of a dry mortar here. This then has a compressor attached to it. Compressed air actually conveys the material from this hopper to the point of application. And it's there where water is introduced to the mix. And it's quite important from the point of the operator's concerned that he's qualified and there is a certification for this. And he'll apply the right amount of water to get the correct amount of build-up in the repair area, but he'll also have the technique to get behind the bars as well. And generally, you can normally sort of judge a good, competent nozzle man, as we call them, just when they start to sort of work on the first part of the repair, because it should work on the bottom and gradually work up, and they tend to be quite active. They're moving around, they're adjusting the nozzle really to get that material in. And then once you get beyond the sort of the surface of the main structure, it's just trimmed off, and then you can apply your levelling mortar or anything, and then any, afterwards protective coatings. So you can see here nozzle man, and there he's getting right behind the reinforcement, and you can see there's not a lot of dust, which is good because it's a dry mortar that's put in to start with, and a good nozzle man will get the water cement ratio really well, so we can actually see what he's doing, which does help, but you know that when that material cures, it's going to be around 55-60 newtons per metre squared. And what they do is they normally do sort of panels outside of the repair area, which they can then be transported to a test house, they can be cored, and they can be crushed to determine the compressive strength. We then have what we call the wet spray, similar machine, but what you do is you put the dry material in first, which is normally bagged, 25 kilos, similar to the dry method. Then water is introduced here, and it's mixed, and then it's then fed to the point of application, again by compressed air, but compressed air is introduced here at the nozzle rather than at the end here, which is what we had for the dry spray. Again, very good if you've got quite a big distance from where you've got the machinery and the point of application. You're looking at around about 20-30 metres. With the dry spray, you can be over 200 metres away from the point of application, which is very useful for marine works and bridge works. And again, you can see here that quite a few repairs here, and the contractor decided that rather than just have a guy doing hand placed, it was actually going to be more productive to actually use a wet method of application, because he could fill the repairs up very, very quickly. And again, it's really a case of when you get to site, sometimes you don't know how big these repairs are going to be, and a lot of it has to come down to contractor choice from the point of view of how he's going to apply that material. What we need to know, what we need to have though, is a selection of products that are CE marked that will actually allow him an element of flexibility, but still comply with the specification of either being structural repairs or non-structural repairs. And then we have the flowable or cast in place material, where you just put a shutter up against the structure, and then you just pour the repair material in, obviously wet, very flowable, so it gets around the reinforcement, and then after a day you strike the shutter and then finish off the repair area here with a levelling mortar. Okay, so what is total corrosion management, or sort of we call it TCM? Well, what we're trying to do with this really is to satisfy the sort of principles and methods for the remediation of reinforcement corrosion. So we're trying to follow the guidelines of 1504 Part 9 really, as Chris emphasised, that's probably the key document when it comes to trying to find a solution to the problem that you have once you understand what that problem is in the first place. So whether we have a situation where we've already need to repair something, we know we can do this, but also we want to avoid it in the future. So what we want to do is have a sort of a toolbox, and depending on the situation, to allow us to keep these areas cathodic rather than turning them into anodic sites and then having this causing a problem again in the next 5 or 10 years. So 1504 Part 9, Looks at barrier coatings or active coatings for protection of the reinforcement once the concrete's been broken out. Also looks at the repair mortars as well, the R1s, 2s, 3s and 4s, but also this method gives you passivity around the bar. Then there's cathodic protection, which Chris spoke about. You can either have an overlay and a titanium mesh connected to a rectifier, and that will protect the reinforcement. Where you can't use a mesh, or you've only got isolated areas which need to be protecting, you can use what we call discrete anodes, and basically they're put into the areas where there can be active corrosion, and they could be sort of placed around different parts of the structure, all connected up again with a similar rectifier, and again can be monitored. So you don't have to always CP the whole structure. Now with this sort of total corrosion management approach, you can use different techniques for different areas of a structure to ultimately give you a very optimized solution to protecting your structure. Then we have chloride extraction or desalination, and Chris has already spoken about that one. And then there's cathodic protection using anodes or galvanic protection, and then there's corrosion inhibitors as well. Then there's hydrophobic impregnations, which can either be silanes or they can be siloxanes, depending on the capillary structure of the concrete, and then there are coatings. So basically these are the techniques which are mentioned in 1504 Part 9 and form part of our Sika Total Corrosion Management portfolio. So I just want to have a look at this sort of simplified corrosion model here. So if you build a structure from day one, in time zero, in theory you've got no corrosion there at all, because as Chris mentioned earlier on, you put reinforcement in the concrete around the reinforcement, pacifies it, it's all sitting there very nicely in this cathodic state. But as time goes on, chlorides can get into the concrete, carbonation can carbonate the concrete. At some stage, things are going to happen to that steel. So we are now starting to sort of see things happening, and this is what we call the initiation stage. And then as soon as we start to get some sort of micro cracking in there as a result of corrosion, we then get into this propagation stage. Things are starting to happen. They can either sort of start fairly quickly and then quickly progress, or they can start quickly but then also slow down a little bit. But there are very telltale signs. You then get macro cracking, right to the point then we get the corrosive products just spawning the concrete. And this is where a lot of the time where people look at the structure and say, right, we've got to do something about it now, rather than do it at this stage. So what we need to do to sort of keep the structure within its surface life, we'll do concrete repairs. We'll put some concrete repair in there, and then we'll walk away and just wait for the next time it starts all over again. But of course now what we can do, we can actually put the repair in, but then what we can do is to start to drop sort of the corrosion model now down into a stage of propagation. We'll never get it back to zero again. Things have already started to manifest themselves, unless you use CP, of course. So what we can do is control it, and depending on the system used and how long you want to extend the life for, then we can apply the appropriate systems, and then as soon as they go beyond their service life, unless you sort of reactivate them again, you're going to get a stage of deterioration, and we'll get back up here. And it could be that it's chosen that, yeah, we only want 50, 60 years out of the structure, so this ends up being 60 years. Whereas it could have been 15 or 20 years, or in the Middle East, as Chris showed, it was sort of 3 or 5 years if you're not careful. So this is where the sort of total corrosion management techniques come into their effect, is once you've done the repair, we've got to do things outside of that repair to sort of protect what's happening underneath the concrete that might not, that is deteriorating, but also can be causing corrosion as well underneath that concrete. So 1504 Part 9, the table here looks at these principles. Chris mentioned it earlier on. We're just looking here at the reinforcement corrosion as opposed to the principles above, which is to do with concrete. And again, all those sort of diagrams that I showed are listed here. Chloride extraction, hydrophobic impregnations there. And what we have is where you have all the principles and the methods, we basically have all the products that satisfy all these conditions in this table. So we've got the repair material, again applied by hand or spray. We've got the hydrophobic impregnations, the coatings. We've got the discrete anodes. We've got the galvanic anodes as well, different sizes depending on the level of chlorides, depending on also possible corrosion rates that you've identified will determine which one you actually use. And then we have inhibitors. Surface applied inhibitors, or we have vapor phase inhibitors where if you've got the problem of corrosion fairly deep down, we can drill into the concrete, apply the inhibitors and they'll spread it through the capillaries of the concrete. Some typical applications. This is a corrosion inhibitor, generally applied, again, after repairs have been taken care of, normally in sort of 2 or 3 coats. And what we can also do, we can actually check the depth of the penetration of that inhibitor as well. It's probably useful to do it at the beginning of the job to ensure that you may have specified an inhibitor, but we also want to make sure that it can actually get through to the reinforcement. So if you know the reinforcement cover, what we do is we take cores and then we go back and we test to see if the inhibitors actually got to the reinforcement. Normally 80 millimetres over sort of 3 months is normally typical. If you're on a bridge where you've got sort of 50 Newton concrete, it can take a little bit longer. But we've also found, of course, if you do it over a few weeks, you can see the progression of the inhibitor as it goes through the concrete. But of course, what we want to do is check behind the reinforcement so we know that it's actually putting this passive film that Chris mentioned onto the reinforcement. And then we have the galvanic anodes, where we have probably, we've got a lot of chlorides and maybe quite a lot of active corrosion where we've carried out the repair. So we've broken out the repair. We've actually prepared the steel as well. And to prevent this incipient anode effect, we will place some galvanic anodes around the outside before we put the repair mortar in to sort of counteract this incipient or ring halo effect. And then for corrosion control, similar to CP, we can apply these sort of galvanic anodes. Zinc being the core. Chris has mentioned that in quite a lot of depth, so I won't go into it, but sort of zinc being the sort of sacrificial metal within the anodes, and then they're encased in quite a strong mortar, so when the zinc gets consumed, you just don't get a hole forming. This casing around these anodes will be part of the repair. So if we start to look at the defects in concrete and sort of remediation of reinforcement corrosion, we can see that an area here we would break out, we then put the repair material in. So principle 1, protection against ingress. Principle 2, moisture control. Concrete restoration, where we use the monotop repair mortars. And then something that we'll cover later on this afternoon will be the sort of structural strengthening, principle 4 and 5. And we've got principle 6, resistance to chemicals, and again we've got a series of coatings that will, if we know what this problem is and the chemicals used, we can apply the appropriate coating system. Because we do get involved in quite a few processes, nuclear power stations as well, where they need quite high chemically resistant coating, so it's a completely different type of, the repair is, and the principles are the same, it's what coating do you put over the top. And then we've got preserving or restoring passivity with the repair mortars, and of course that happens with at this point here. And then we've got increasing resistivity, cathodic control, and all of these really, principles, quite simply covered by these here, either by coatings and also by inhibitors as well. So you can see that by just doing one action, you can actually cover quite a few principles within 1504. And principle 10 is cathodic protection, which Chris has covered, and then there's the inhibitor process as well. So when we start to look at total corrosion management, it sort of comes under this umbrella of electrochemical protection. And for carbonation, it's fairly simple to resolve. You do your repair, and then you just apply the inhibitor over the top, because generally your corrosion rates are very, very small in carbonated concrete, and the corrosion is more generalised. Ferrogard will normally sort of solve the problem, and then it's just a case of putting a coating over the top for aesthetic reasons, but also to stop that carbonation front advancing any further, but also to try and stop moisture and oxygen getting through and drying out, so we need to dry out the concrete. So we're sort of looking at a synergistic effect of not only the Ferrogard or the inhibitor, but also the coatings as well, drying out the concrete. Sort of bring these sort of corrosion rates down to an acceptable, controllable level. When we've got chlorides, then obviously it's a completely different game altogether. So if we look at principles 11, we've got the Galva shield anodes here, and again the zinc, with the zinc sort of sacrificial metal being there. We saw that earlier on in the photograph. Then what we have is the Ferrogard as the inhibitor, and then we've got cathodic protection and a series of other sort of galvanic products as well to satisfy those principles in 1504 Part 9. So Chris mentioned trying to identify, or having to identify, what the problem is to start with. An element of testing goes on. Once we know what the problem is, then obviously we can attack it with the various total corrosion management solutions. And typically, if you start to look at a car park where perhaps you've got the sort of the parapets and the external envelope being, the reinforcement being sort of corroded due to carbonation, then you'd approach that typically with an inhibitor all around. But then when you start to look at the car park decks, which generally will have the chlorides on, you'll have chloride depths and concentrations at various levels on the decks. And generally on the first sort of 2 to 3 levels, they're quite sort of very concentrated. Your corrosion rates will be quite high, so you'd then possibly look at maybe some sort of cathodic protection system on those levels. But then as you get higher up, the chloride levels tend to drop, and also the depths tend to drop, so then you can start to think, well, do we use galvanic, do we use inhibitors? And generally when you get to the top levels, you tend to satisfy yourself, you can actually use inhibitors. So again, you can use different systems for different situations, but you can come up with a very bespoke solution using total corrosion management. To help you, and part of your sort of giveaway on the sort of memory stick is a few brochures in there, and on our total corrosion management brochure, in the back there you'll find a product selector. So we've got all our systems on here, and what we've done, we've actually started to look at carbonated concrete. So if you've got carbonated concrete, these are your choices. If you've got chloride-induced corrosion, depending on the chloride level, you then use one of these systems. So it makes it very simple for you to select. We're not saying that you shouldn't sort of take advice like experts like Chris Atkins, but at least it gives you a starter for 10. And also this obviously helps the contractors if they're have a project and they really want to see what they can do to give an optimised solution, then they can use this as well. But ultimately, talk to us as well. CE marking, Chris mentioned it, we have to spend a lot of money on testing. It's all laid out in 1504, but ultimately what you see on packaging, whether it's a coating or a bag of repair material, is the CE marking. That's the first thing really to look at. And then what you have here is a number, which is the identification of the notified body. In our instance, the BSI, our notified body, they audit everything, they do quite a lot of the testing for us, and therefore you could always refer back to that notified body, as well as ourselves, for information on all the testing that's been carried out. Then there's where the product's made, what year it was made, also the certificate number, the declaration of performance certificate number, which we'll come on to in a moment, And then just really a sort of brief summary of the characteristics of the product and whether they pass the requirements of 1504. Declaration of performance is the actual certificate that we produce for each product, which is sort of a more of an expanded version of the CE marking that's on the packaging. And this gives you all the different test methods that we used, exactly the same tests that were carried out that you have to comply with 1504, and this information will be on the packaging as well, but it won't have the sort of test methods on there. So you're well within your right to also ask a contractor, you've got this material that says it's CE marked, but also I'd like to have the physical documentation, if nothing else, to justify why I've selected the material, and secondly, that it complies with 1504. And then it has to be signed off by the relevant sort of people within the company that have that authorization to say that this has been carried out with these tests. Okay, just to round up then, just a few selection of case studies that I've chosen that I hope to give you a flavour of what systems we can use for different situations, but also to give you an insight of how you can monitor structures, not only to test the inhibitor, but also their long-term effectiveness as well. This was a project in Wales, the Olympia House Passport Office. A lot of the cladding, cladding on the side on the building. There was a stairwell here, and this tended to have quite a few chlorides in because they salted the stairwells, but predominantly it was generally sort of chlorides. So we repaired it with monotop systems, which were the R3, R4 products. Then we applied the inhibitor over the structure, and then we applied an elastomeric coating because there were quite a few signs of cracks that had been identified but weren't contributing or been contributed by corrosion. So it was just sort of the way the sort of the panels had been constructed, and the structure was actually monitored. It was a government building, so they wanted to see that whatever had been proposed was actually going to work. So there was quite a few levels and quite a few readings around the building. This is just typically one of them. And we were finding that on part of the building, we've got about 158 microns a year of corrosion products that were being formed. Now, Chris mentioned using half cells, which really aren't appropriate for carbonated structures, but also with half cells, when you start to look at BRE Digest 444, which clearly outlines quite a few of the electrochemical sort of monitoring techniques, there's criteria there, and basically half cells is all based on probability. It may or may not happen, and it may happen over these years, but it's not really that conclusive. Another way of doing it is to look at linear polarization methods, which actually measure the actual corrosion loss on the steel. I'm an engineer, I can refer more to how much steel's been lost than sort of what voltage is going through a piece of reinforcement. So this to me is a bit more meaningful. So this is you losing 158 microns of steel per year. And in BRE Digest 444, particularly with some of the criteria there, then this is quite high. You know, things are happening now, and unless you do something about it, you're going to get sort of concrete spawning off. So we did some pre-treatment in these areas. After a week, it dramatically took this to 4.5 microns a year. So we're in the sort of relatively safe zone. So it just showed you how porous that concrete was for the inhibitor to get through the concrete and onto those bars. Then after 15 months, it'd done obviously a lot of work in the first week, and we were down to 3 microns a year, and then after 3.5 years, 1 micron a year. So this has really controlled it from this level down to this level. And of course, as time goes on, it would just continue along here. What we can't do with inhibitors is stop corrosion, unlike CP, which you can. But what it does, it controls corrosion to acceptable levels where you probably won't have to do anything for about 10, 15, 20 years. This is another project. This is in Southampton. Again, low cover, carbonation. Tends to be a lot of the buildings that we do sort of come up against mostly within our business. So again, monotop repairs, inhibitors applied to the structure, penetration test, which I sort of discussed earlier on, where we can measure the penetration of the inhibitor to make sure it's right for the job to start with, and then elastomeric coatings over the top of the structure. Southampton, again, Itching Bridge. You would have thought it would be a sort of chloride issue here, being in a marine environment. It was predominantly carbonation. The concrete was actually in quite good condition, apart from the half joints here. So basically they applied the inhibitor over the whole structure, and as a sort of an additional sort of protection to it, they applied silane around the column heads as well. Car park, I've sort of mentioned earlier, sort of how we sort of treat car parks. In this situation, the chloride levels on the decks weren't particularly high, so we managed to use the inhibitors on the decks. But of course, if they were really into the range of 1, 2, 3%, and issues with low millivolts from half cells, then obviously it would be a completely different game altogether. We'd probably have to look at CP or sort of galvanic protection. This is Highways Agency Road Bridge, chloride-induced corrosion. They were looking and being very interested now in this sort of corrosion inhibitor technology. So they said, well, okay, come along, we'll get somebody to monitor it, you apply it, and we'll see what happens. And what happened was that there were some sort of impressed discrete anodes placed again around the half joints, but then we coated all these other areas with the Ferrogard. And you can see here, you're at 24.5 microns loss of steel per year. But by applying the inhibitor, we got it down to 6.4 microns a year in quite a short amount of time. Again, this is another Highways Agency bridge. They don't just like to look at one bridge, they like to look at 2 or 3 in different parts of the country. Again, chlorides was a problem here. All the trestles underneath the bridge, underneath the deck, half joints. Chris mentioned it, seems to happen on lots of bridges, always a problem, but then it tends to, all the chlorides tend to sort of dribble down and get taken up in the columns and the beams. So here was, we applied 903. You can see that the different areas that we applied the inhibitor at and that were tested. You've got about 54 microns loss of steel here. We took it down to 0.6, 26 to 0.3, 3.6, not particularly high, sort of acceptable, but again, made a big difference, and 0.8. But I think, you know, when you start to look at these and seeing the sort of the order of magnitude that we're taking it down to, again, we're not taking it down to 0. You know, that's the important thing with this sort of corrosion management, and the same with the galvanics, is, you know, unless you've got CP, really it's what's controlling corrosion, we're not stopping corrosion. I think that's the big thing to take away today from this morning's presentations. An incinerator chimney, you can see the height and diameter there. Chloride-induced corrosion on the sort of the outside and the inside, and monotop repairs, inhibitor applied internally and externally, and then a Sika guard coating placed on the outside and a chemical resistant one on the inside. 1 month's evaluation of the structure. Base of the chimney, it was around 9.1 microns a year. We took that down to 1.5. This is so after 1 month. As time goes on and you get more film around the reinforcement, you get greater suppression of corrosion. Middle of the chimney around about 22.8 down to 7, and the top of the chimney, which you'd expect around about 39 down to 4.3 after 1 month. So again, fairly impressive results. In the States, they use the same product. Again, they just happen to use the same testing house with the same equipment to go and measure some, do some testing over there, and again, very similar results. You can see down from 50.5 to 1, 7.9 to 1.7, but nothing going to 0 with the use of the inhibitors. But again, controlling that corrosion on the reinforcement. So this is Union Carbide headquarters, parking garage, so there's elements of chlorides there and half joints you can see here, and lots of leakage of water and chlorides, and they're at levels which are controllable by the Ferrogard, so the whole structure was covered in the inhibitor. This is in Switzerland, the bridge, mainly carbonation rather than chlorides, and again very simple solution, application of the inhibitors. And then in Switzerland, they didn't want to coat the structure, but they wanted a sympathetic solution, and basically if you apply the inhibitor, because it sort of impregnates into the concrete and affects the reinforcement, it doesn't affect the outside of the structure. So as it was exposed aggregate, they wanted to keep the sort of same character of the building, then that was the solution, and then we just put a clear coating over the top to sort of help dry out the concrete and also sort of reduce the moisture that was getting into the concrete. And Germany, this is a water treatment plant. This can cause a few problems, certainly where you've got the soffit of the structure, gets a lot of condensation on there, a lot of attack there, carbonation. But of course, being water, they don't want to use systems that are going to contaminate the water and cause problems further down the line to people's health. And that's the advantage again of the inhibitor that we have. It's water soluble, and it doesn't cause any problems if it does fall into the water. It's not carcinogenic, and it's very easy to use and good for the contractors as well. And the last one, a bridge in West Yorkshire, very high chlorides, no option really than to do the repairs and use Sika Galva Shield on there, which was the anodic anodes. So just to conclude really, hopefully now you've seen our approach to total corrosion management. You can see how it can provide sort of very cost-effective and optimised solutions for extending the life of structures. We're the only company in the UK that has this approach, and we're probably the only Sika company in the world that has this approach as well. In association with trained contractors, we stand behind what we say now with this approach, and we're quite prepared to give 20-year guarantees now on these systems. This is when loads of people write 20 years guarantee, they'll write lots of notes on that one. So at this point, I'd just like to thank you for your attention.